we're going to look at the situation where, and this will come up in many problems along the way in on AP exams and so forth. We're going to look at the situation where we attach one end of a spring to a wall or something over here. Here we'll do this. So we attach one end of a spring to a wall or something like this over here. This squiggly thing is supposed to be a spring. And we'll just say that this is its unstretched length. It's just hanging out there. And we're going to eventually attach this block over here to it and look at it. We'll say compress it. I'm going to let it go and let it oscillate, is the word we use, back and forth. And we want to look at the force that the spring applies, the energy, both kinetic and stored in the spring, the acceleration, the velocity. There's a lot to look at, which is why it shows up on the AP exam, because there's a lot of physics involved here, not just the springs. So let's start off with this. Our spring can be compressed or stretched, and in this problem, to simplify things, we call the spring massless, so none of the force or energy goes into moving itself. It just has to accelerate the block. And we keep things simple by saying that this surface has no friction. A more complicated situation, but one that you'll also be expected to handle, is over here. So here we have similar situation with an object oscillating on a spring, except there's another form of energy involved here that isn't involved in the other one, and that is gravitational potential. So not only do we have kinetic energy and spring energy, we also have, because of the change in height, gravitational potential energy as well. So that complicates matters a little bit, but for this initial situation, we don't have to worry about that. Everything's horizontal. So some things that we know. Even before we put the block on there, if this location that we've marked is where the spring is now, is the equilibrium position, we call that spot x sub 0. And it is assumed generally that that will be 0 meters. It doesn't have to be, I guess, but if you have a choice, you might as well. That means, of course, all the values for x over here are going to be negative, and all the values for x over here should be positive. And I'm not overly worried about the positive or negative right now, but it's something to keep in mind. So, what about the force by the spring at that location, at the center there? At that equilibrium position, what about the force? Well, if the spring isn't stretched or compressed, it's not applying a force. If x is 0, then the force by the spring is also going to be 0. And it is probably a good thing to note right now that since the spring is really the only possible thing for a net force, there's no friction, and of course when we put the block up there, normal force and weight will cancel each other out. So the force by the spring in this case is the net force. Well, if that's the case, what does that mean about acceleration? So no matter when the object, even if it's moving past that point, the acceleration has to be 0. Because acceleration doesn't really depend on velocity, it affects velocity. But what acceleration is created by is this net force. And if that, let's point that out real quick, remember this is going to be, for this situation, this will be the net force. And if that is 0, well then the acceleration has to be 0. So those things will be true, and there'll be other things that we'll add to it as we go along. So let's start this thing off. We're going to take our spring, and we are going to compress it. Smash it down to there, hold it there for a second, and attach the block at that location. And the arrows are really just there for me as a reference point. And we're going to let it go. But before we do, what kind of energy do we have here? Well, let's start with this. What is our position? There is a specific name. We'll do this in green. There is a specific name for the position at that point. This is the farthest it's going to be stretched in either direction. And it would stand to reason, by the way, that when it leaves here and goes all the way to the other end, that the distance I stretched it, by conservation of energy, we'll look at it, should be the same as the distance it goes out. It would make no sense if you compress it a certain distance and it flies past that over here. You'd have to ask yourself, where did the extra energy come from? And we know that unless somebody pushed it or something, or has a little engine on it or something, that energy is not coming from anywhere. So all the way out here at the extreme end, we call that distance the amplitude. The farthest distance it goes is the amplitude. In this case, I'll put a negative in front of it. And out here, when it gets there, I'll call it positive. But the farthest distance. So when it's here, we wouldn't call x the amplitude. It would be some other number. And whatever that amplitude is, it will not exceed that for this situation. So we call the x position out there the amplitude. Let's start talking about the force. What about the force by the spring, which remember is also the net force? Well, as I move it this way, that force increases and increases and increases. And this is as far as I move it, this is the strongest that force is going to be. So we have out here the maximum. This force will be at its maximum for the entire thing. That's as strong as the force is going to get. Well, wait a second. Let's keep the same logic we had over here. If the net force is 0, and so acceleration has to be 0, then what about if the net force, remember, spring, it's also the net force in this case. If the net force is at a maximum, it would stand to reason that acceleration will also be at its maximum out here. What about velocity? Remember, I stretch it out there, I'm holding it just before I let it go, or right when I let it go. What's its velocity? Yeah, you're right. It's 0. I'm holding it there, right? And when I let go, its velocity out here is going to be 0. Speed, velocity, yeah, we'll call it velocity. It'll be 0. So this brings up one of the things that drives people the craziest with this, and that is when the velocity is at its minimum, when it's as slow as it's going to go, 0, the acceleration is at its maximum. It is undergoing its strongest net force and therefore its strongest change in velocity. It was, in this case, well, later on we'll look at it, it'll be, as it comes into that position, it'll have a negative velocity, and as it leaves, it will have a positive, but at that moment, the change in velocity will be its largest. So what about the kinetic energy out there? You think velocity, you think kinetic energy, you got to think velocity. And that's why I brought it up first, because the kinetic energy out there, if the velocity is 0, kinetic energy is 1/2 mv squared. If v is 0, you've got no kinetic energy. What other type of energy do you think is there? Well, we're dealing with springs, right? So the other type of energy is the potential energy in the spring. Now you got a choice. What do you think it is? Maximum or 0? Because really, out here at the extreme end, it's one or the other. And you would be right, if you think about it, if the kinetic energy of spring is 1/2 kx squared, we are at the biggest k we can get, the biggest x we can get. The k is a constant for the spring, of course. We have 1/2 k the amplitude squared, which by its nature, and this isn't an important formula, so to speak, to remember, what you really want to know is that spring has got as much energy stored in it right now as it's ever going to have in this situation. So we are at a max. In fact, I'm going to erase this and just boil it down to, at this point, we have maximum. So if we knew how far it was stretched and we knew the k value for the spring, or in this case compressed, I should say, and we knew the k value for the spring, we could find that amount of energy. All right. So we let it go. It starts to accelerate and move in this direction. By the time it gets back to where it started, so by the time it gets to here, what's true about it? What else? Now what do we know about it? First of all, unlike the beginning situation, we should all recognize that at this point, that thing's moving, right? It's moving from left to right. And it doesn't, even though the net force on it at that point is 0, that doesn't mean it stops. That just means there's nothing there to stop it. It's just going as fast as it's going to go. It blows right through the equilibrium position. But what does it start to do just on the other side? Well, the spring starts getting stretched. It starts pulling against its motion. So while we don't have an acceleration or net force here, we will anywhere over here. And in this case, as it moves left to right, it'll slow down. So at this moment, it is going as fast as it possibly can be going. Its velocity is at its maximum. What about the kinetic energy? Well, it's at a maximum because it's linked to velocity. What about the energy stored in the spring? Yep, it's at this 0 position, so the energy stored in the spring is 0 joules. Now, conservation of energy, we mentioned it a little bit. If there's no friction for it to go to heat energy, anything, what do you think must be true about these two numbers? If you had, let's say, 100 joules of energy stored up when you were at this location, when you get to here, if none of it went to friction, you should still have 100 joules of energy. And now, since it's no longer in the spring, all 100 joules of energy by conservation must be somewhere. And if there's no energy that goes to heat, it's got to be this. You'll have 100 joules of kinetic energy at that point. So you know where this is headed, because when we get out to the other end, when we take this thing all the way out and it stretches the spring and the spring starts pulling against it, eventually the spring will stop it. And when it stops it, what's true? So what do we know about that end of the world? See, if I were you, I would pause the video and make some conjectures for yourself as to what's going on at that point. What do you know at that point? So, pause it and come back. Welcome back. So, you're all the way out at your positive amplitude. The force, the net force, which is the force by the spring in this case, is going to be at a maximum, right? It's pulling as hard as it can pull. It'll be the same force that you see here. It's just pulling the other direction because it's stretched instead of compressed. What else do we know? Well, if its acceleration, if velocity is at a, velocity, if its force is at a maximum, its acceleration must be at a maximum. But out here, we've already mentioned that it stops, so its velocity is 0, and therefore its kinetic energy is 0. And lastly, all that potential energy is back. All that energy, potential energy that it had here has spent some time as kinetic, and then is now back in the form of all potential. What about in between? So I just made up a number a minute ago. I said, what if it had 100 joules here? This would have to be 100 joules here, because there's only two places energy can go in this situation. Kinetic energy, or the energy in the spring. So out here would be 100 joules. What about somewhere in between? What about right in here? We'll say in blue. So what about this spot? There's going to be a split. I would not assume at this point that the split, just because I've drawn it roughly halfway between the two ends here, the middle and the end, I wouldn't assume that it's split 50-50 at that point. There's some squareds involved here in both kinetic energy and potential energy. So I'm not convinced that the middle position has the middle energy. Is where they split the energy. But what do you know? If I knew if one of them was 60 joules, I don't care which one, what would the other one have to be? So if there were 60 joules of kinetic energy in there, how much energy is in the spring? Well, conservation of energy says you can't lose that 100 joules. So at any given point, you still have to have a total of 100 joules. And so if you know that the kinetic energy is 60 joules, that must mean the spring energy must be 40, because the sum should stay the same. And we're going to discuss it in a later video, but good moment to introduce it now. If you have the sum of all potential and kinetic energies for a system, an object or a multiple object, is called the mechanical energy. Of the system. So keep that in mind. The sum of, usually it's spring energy plus gravitational potential plus the kinetic energy is what we call the mechanical energy. And so in this case, we would say the mechanical energy is conserved because there's no friction, and it always has to be that arbitrary number of 100 that I happen to make. All right, I think this runs through. Knowing the transitions there, knowing the, you could be asked a question, and when it's here, when that object right here is at this location and moving this way, could you answer a question saying, hey, which way is the net force acting on it? Which way is the acceleration? Which way is the velocity? Or when it goes past that point and is still headed this way, could you give the same kind of questions? Ask yourself at any location there, depending on what direction it's moving, because that makes a difference. What's the velocity vector look like? What's acceleration look like? What's net force look like? And so on and so forth.